Fine-tuning large language models, like GPT-3 with 175 billion parameters, is costly, requiring massive GPU memory and weeks of training. Each specialized model requires a full, expensive training run, creating a new large model copy that needs its own serving GPU. This compounding cost is what LoRA was designed to address. LoRA fine-tunes models by observing that weight updates are low rank. It freezes the original weights and injects two small trainable matrices into attention layers. Their product is the update added during inference. The rank, typically 4, 8, 16, sometimes 64, drastically reduces trainable parameters, up to 10,000 times fewer than the original dimensions. A scaling factor, alpha, controls the update strength. This approach prevents catastrophic forgetting, preserving the base model's knowledge, and the adapter itself is only a few hundred megabytes.
An adapter is not a model. It's a lightweight patch, a set of small matrices that modify the base model's behavior when loaded. The base model never changes, only the adapter is swapped. This is what makes the whole platform possible. One base model on one GPU, 7 adapters, each fine-tuned for a different task. Load the SQL adapter, the model thinks like a SQL expert. Swap to the Flutter adapter, it thinks like a Flutter developer. The swap happens at runtime, in seconds, without restarting anything. It's also worth noting, each adapter is only compatible with the specific base model it was trained on. All 7 of ours were trained on the same base, so compatibility is guaranteed across the platform. That is the foundation. Now let's look at how we configured the infrastructure to make it work.
The cluster is running RKE2, utilizing a Helm-based Kubernetes stack. MetalLB for bare metal IP. Envoy Gateway as the core proxy. Envoy AI Gateway for AI-specific model-based routing. AI Bricks, managing the model lifecycle via the model adapter resource to integrate LoRA adapters. The deployment runs the base model, Qwen, on vLLM. 3 things are non-negotiable here. The label on the deployment, enable LoRA in the vLLM arguments, activates the LoRA engine at startup. Without it, nothing loads. And vLLM allow runtime LoRA updating equals true. This separately unlocks dynamic load and unload at runtime via the API. The AI Bricks custom resource, point it at the base model, give it a pod selector matching those labels. It loads the adapter weights into the running vLLM pod with no restart, and automatically creates a headless service for that adapter. The backend and AI service backend register that auto-created service with Envoy and declare it speaks the OpenAI protocol. The AI Gateway route is the routing table for the whole platform. AI Gateway reads the model field from the request body, maps it to the model header, and the route matches on that. After applying the manifests, we can confirm everything is wired correctly. kubectl get model adapters shows all 7 adapters running. The model path column shows the exact Hugging Face source each adapter was pulled from. kubectl get AI Gateway route confirms the route is accepted. At this point, the cluster is serving 7 distinct AI endpoints through a single gateway on a single GPU with a single base model. The gateway exposes a standard OpenAI-compatible v1/models endpoint. One curl to the load balancer IP returns all 7 model IDs, the base model, and each of the 6 adapters, all owned by the Envoy AI Gateway. This is the proof of concept at the infrastructure level. Now we send the same prompt to both the base model and the SQL adapter. The prompt, find duplicate emails in a users table. The base model response is correct but generic. The SQL adapter response is precise. Envoy routes to the same vLLM pod either way. The adapter delta is what changes the output, applied at inference time to the frozen base weights.
Let's start with SQL. Same prompt to both. The base model gives a working answer, but look at the approach. It wraps the aggregation in an unnecessary subquery. The SQL adapter cuts straight to it. Second SQL prompt. The base model gives generic advice about indexes. The SQL adapter returns an actual query, real table aliases, a specific date function, join conditions written the way a database developer would write them. It's not describing a solution, it's giving you one. Now, Flutter. Same prompt, a product card widget with state management. Both produce a working stateful widget. But look at what the Flutter adapter adds: quantity management with increment and decrement methods, card elevation, proper box decoration on the counter, and crucially, it includes the full product class definition that the base model leaves out entirely. Second Flutter prompt. Model appends new data to the provider without clearing the previous state first. The Flutter adapter clears first, then updates. That's a subtle difference, but it's the correct pattern. Without the clear, you accumulate stale data on every fetch. Not a different model, not a bigger model. The same 1.5 billion parameter base with a few hundred megabytes of LoRA weights changing how it responds. Same GPU, same endpoint. Model name in the request, that's the only switch.